All right, continuing on. The next portion of section 4.6 is on kind of a very related concept to Half-Life, which is instead doubling time. So, doubling time is the time that it takes for a quantity to double. So, this time, instead of having 1/2 equals b to the t, we have 2 equals b to the t, or they wrote b to the x here. So, very, very similar, very related problem. Looking at this example, cancer cells sometimes increase exponentially. If a cancerous growth contained 300 cells last month and 360 cells this month, how long will it take for the number of cancer cells to double? So there are a few ways of doing this. Let's say that t equals 0 is this month, because this is the present, right? Let's say t equals -1. This represents going into the past, right? So let's say that is last month. This gives us 2 points. It gives us the points 0, 360, right? 360 cells this month, and -1, 300. There were 300 cells last month. So from this data, we can find an equation for this growth. We know immediately here that A, our initial value, is going to be 360. This gives us that C of t is going to be 360 times b to the t power. If I substitute in this other point that I have, then I get 300 equals 360 times b to the -1. This gives me 300 equals 360 over b. Multiplying both sides by b, I get 300b equals 360, and then dividing both sides by 300, I get that b is 360 over 300. This simplifies to 6/5 or 1.2. This gives us the equation C of t equals 360 times 1.2 to the t power. If I want to find doubling time then I just want to set 2 equal to 1.2 to the t power, right? I just want 2 equal to b to the t. Taking a logarithm of both sides, I get natural log of 2 is equal to natural log of 1.2 to the, or I can go ahead and use my exponent rule, t times natural log of 1.2. This gives me that t is natural log of 2 divided by natural log of 1.2, which is about 3.802 months for the number of cancer cells to double. Another example here. Use of a new social networking website has been growing exponentially, with the number of new members doubling every 5 months. If the site currently has 120,000 users and this trend continues, how many users will the site have in a year? So we can use doubling time to find a function that models the number of site users and then use that equation to answer this question. We could use some arbitrary a here for an initial value, but we actually know that our initial amount is 120,000. So let's say that this equation will measure the number of users in thousands after t months. So we can set up an equation that looks something like n of t equals 120 times e to the rt. Using a continuous growth model is often a very good idea for things that are constantly growing or changing, like populations. And I think that growing social media or a growing social networking site would definitely fall under that. So I could simplify this a little bit, right? This says the number of new members doubles every 5 months. So actually this 120 doesn't matter, right? What I really want here is 2 is equal to e to the 5r. This will let me find my growth rate. Right, this is my doubling time equation here. This will let me find my growth rate. And then I can find how many users the site will have in 1 year. So from here, I take the natural log of both sides. I get natural log of 2 is equal to 5r times natural log of e. So natural log of 2 is just equal to 5r. Or r is equal to natural log of 2 over 5. Which is about 0.13... Oh, that didn't write well. 0.1386. So now our equation for the growth of this social media or social networking site is n of t is equal to 120. Again, this is going to give us an answer in terms of thousands of users, times e to the 0.1386 t. So if I want to find the number of users in 1 year, this would just be the same as plugging in 12 for t, right? This gives us 633.140. And our answer here is in terms of thousands. So after a year, we would expect 633,140 users of this social media site. Let's look at Newton's law of cooling. When a hot object is left in surrounding air that is at a lower temperature, the object's air temperature will decrease exponentially, leveling off towards the surrounding air temperature. This leveling off will correspond to a horizontal asymptote in the graph of the temperature function. Unless the room temperature is 0, this is going to correspond to a vertical shift of the generic exponential decay function. So Newton's law of cooling is the temperature of an object T in surrounding air with temperature T sub S will behave according to the formula A, or T of T, is equal to A times E to the KT plus T sub S, where lowercase t is time, A is a constant determined by the initial temperature of the object, and K is a constant, which is the continuous rate of cooling of the object. So the continuous growth form of this is the most common form. Here's actually a pretty good application. A cheesecake is taken out of the oven with an ideal internal temperature of 165 degrees Fahrenheit and is placed into a 35-degree refrigerator, which I don't recommend doing. You should leave this should cool to room temperature a little bit before you throw it in the fridge. But anyway, after 10 minutes, the cheesecake has cooled to 150 degrees. If you must wait until the cheesecake has cooled to 70 degrees before you eat it, how long will you have to wait? Well, since the surrounding air temperature in the refrigerator is 35 degrees, this means that our T sub S in our equation is going to be 35. Our initial temperature was 165 degrees, right? Whenever it comes out of the oven, has an initial temperature of 165 degrees. So far I have what? With just this T sub S bit of information, I had T of T is equal to A times E to the KT plus 35. I then know that T of 0 is 165, meaning that 165 is equal to A times E to the K0 plus 35. This means that 165 is equal to, let's see, this just becomes A because this is E to the 0th, which is 1, plus 35. Subtracting 35 from both sides, I get A is 130. I was also told that after 10 minutes, the cheesecake had cooled to 150 degrees. This means T of 10 is 150. Or that 150 is equal to 130, this is A, times E to the K times 10 plus 35. Subtracting 35 from both sides, I get 115 on the left-hand side. This is equal to 130 E to the K times 10, or 10K. We'll write it as 10K. Dividing both sides by 130, I get E to the 10K is equal to 115 over 130. Taking a natural logarithm of both sides, I get that. So just to clarify, I'm taking the natural log of both sides now. I get that 10K is equal to natural log of 115 over 130. That K is equal to natural log of 115 over 130 divided by 10. Which is about negative 0.0123. This means that our equation for cooling is T of T equals 130 times E to the negative 0.0123 T plus 35. And I want for my temperature to be 70 degrees before I can eat it. So I'm replacing the left-hand side with 70. Now I can actually solve for T. I can solve for the amount of time that it will take, and this is going to give me an answer in minutes, in order for my cheesecake to be eatable, I suppose. Not necessarily edible, right? Anyway, subtracting 35 from both sides, I get 35 equals 130 e to the negative 0.0123 t. Dividing both sides by 130, e to the negative 0.0123 t is equal to 35 over 130. I can then take the natural log of both sides, and I get negative 0.0123 t is equal to natural log of 35 over 130. Where that t is natural log of 35 over 130 divided by negative 0.0123. And this is about 106.68 minutes. If we were rounding to the nearest minute here, we'd say about 107 minutes. Or 1 hour and 47 minutes for the cheesecake to cool to 70 degrees. Realistically, you should probably just let it come to room temperature and then throw it in the fridge overnight. It's easier that way. Don't worry about having to do all this math. Not for a cheesecake. All right, that's it for doubling time and noodle dissolved cooling.